Hello friends, in this video we are going to get introduced to a very important concept in metric spaces, that is the idea of open balls. So before we actually learn the definition, let us have some revision of the continuity, the definition of continuity, which actually has a base of the concept of open balls in it. So let us recall what is the definition of continuous function. So if I have a function f from say r to r, I am just taking from reals to reals because you have studied reals to reals continuity. Let us fix up some point p in r, and what we say is f is said to be continuous if for every epsilon greater than 0 there exists some another real number delta positive such that whenever mod x minus p less than delta, that is whenever x is within delta distance from p, we must have its image f of x to lie within epsilon distance from f of p. So if you observe carefully, what we are saying here is we are saying that for all those x which are lying within delta distance from p, something should happen. Now this collection, this set of all points which are lying within delta distance from p, this set is actually called as an open ball with center p and radius delta. So more precisely, let me give you a definition now. The definition in general can be for any metric space X. So let me take a metric space X with a metric D on it, and let me fix up some point say p in that space. Let us take some r positive, a positive real number. I want to talk about open ball which is having center p and radius r. The general notation is b p comma r, and now as I said, it is the collection of all points from my space which are at a distance less than r from point p. So how do I write it as a set? It is set of all points in capital X in the space X whose distance from p, that is dx comma p, is less than r. So this is what the definition of open ball that we have. Now once we get introduced to the definition, let us have plenty of examples in fact to deal with and to understand what the idea of, what the open ball means. To start with, let us begin with the simplest one, the one which we all are very much familiar with. Let me take set of real numbers and let me take D as usual metric. Now we already have studied what is a usual metric, still let me just write down. So it is the distance between any two real numbers x and y is simply mod of x minus y for every x and y in R. So this is the metric that I have, and let us figure out how the open ball will look like in this particular metric space. So I would like to work in general. Let us take any real number p and any r positive, then BPR by definition what we have is all those real numbers for which the distance between x and p is less than r. But we have definitely studied that this set is nothing but an interval which is open interval p minus r to p plus r. This simply can be proved using the properties of mod. So this is the very first example and very simple example that any open ball in the set of real numbers with usual metric is going to look like a open interval p minus r to p plus r. So let us consider another example with the same set, that is set of real numbers, but this time I am going to change the metric. So let us see the example. I am taking x equal to r and the metric is dxy is equal to mod x minus y upon 1 plus mod x minus y. Now let us see what happens to different open balls in this particular metric space. So to begin with, let me take a simple one, that is b 0 comma half. So I want to know now how this b 0 comma half looks like in this particular metric space. So, by definition, let me quickly apply the definition. So, it is set of all those real numbers for which the distance, now it is a new distance of 0 of any x from 0 is less than 1 by 2. So, let me write it, distance of x and 0 less than half, but this is equal to, if I quickly figure it out, then I am going to get it as mod x upon 1 plus mod x less than 1 by 2, that is all the real numbers which satisfy 2 mod x less than 1 plus mod x, which is x belongs to R, for which mod x less than 1. And then you can see that it is nothing but a open interval minus 1 to 1. So, if you see it carefully or if you observe carefully, in the earlier metric, although the set was same, because the metric was different, the structure of open ball changes. So, in the earlier example, the same open ball b 0 comma 1 by 2 is going to be minus half to half, whereas here for this particular metric it is changing to open interval minus 1 to 1. Just to get the idea of this metric more, I would like to deal with 2 more open balls with respect to the same metric. So, let us try to figure out how will the structure of those open balls looks like. So, let me take the same set and the same earlier metric. So, I am not writing the definition. Now, I want to discuss what is the open ball b 0 comma 1. Now, what it will be? It will be all those real numbers who are going to satisfy this mod x upon 1 plus mod x less than 1. Now, what do you think, which all real numbers are going to satisfy this? That means I want mod x to be less than 1 plus mod x. Yes, what your guess is certainly correct, that is every real number satisfies this, because for any real number mod x is always less than 1 plus mod x, and hence what I am going to have is b 0 1 is the set of real numbers full. So, let us consider some more examples in the same metric with different points. For example, if I now try to work out b 0 comma 2, then I am sure you could have guessed the answer, that it is again going to be R. In fact, more generally I can make a statement that if I look at BPR, then it is going to be full R for any R bigger or equal to 1. So, for each R, if I take it as 1 or more, then the open ball will be the full metric space. Now, let us go for one more example. I am just taking the same set, but changing the metric again. So, I am taking now x equal to set of real numbers, and the metric what I want to deal with is discrete metric. Okay. Now, we already know how a discrete metric behaves. It is going to give me the distance 1 if the points are different, and if the points are same, I am going to declare that the distance between them is 0. So, if I ask what is b 0 comma 1 by 2, then it is nothing but all the real numbers for which the distance between x and 0 is less than half. But we know that distance between x and 0, there are only 2 values for this, that is it can be either 0 or 1, and since it must be less than half, it cannot be 1, and hence the only option that is left out is 0. Hence, we must have distance between x and 0 to be 0, and hence I get singleton 0 as this b 0 comma 1 by 2 equal to. So, this open ball is a singleton set, whereas now if I ask what is b 0 comma 3 by 2, then it is going to be all the real numbers which are satisfying this condition dx comma 0 less than 3 by 2, and now dx comma 0, as we know, it has just 2 values 0 or 1, and both of them are less than 3 by 2. That means every real number is going to satisfy this condition, and hence b 0 3 by 2 becomes R. So, the general structure of open ball in this particular metric space is going to be, you take any BPR, then it is going to be singleton P if 0 less than r less than 1, and it is going to be full space, that is R, if R is greater than 1. What is going to happen for R equal to 1, that you can actually check it out, that you are going to have here dx0 less than 1, and hence it is again going to be singleton P. So, in general I have BPR to be equal to singleton P for R less than or equal to 1 and full space R for R bigger than 1. In the next video, we are going to deal with the structure of open balls in some more metric spaces like R2 or set of continuous functions, etc.